Hi, my name is Julien Jomier. I'm leading the software solution team at Kitware, and I have been involved with CMake since pretty much its inception about 20 years ago. And I lead the development of C-Test and C-Dash. It's a pleasure for me to be presenting at Meeting C++ this year. So my talk is going to be about CMake. If there are some of you that are not familiar with CMake, I'm going to describe a little bit how what CMake does and what CMake is. I will also talk about CMake and the support for C++20 modules. And at the end, I will talk also about CMake dependency handling, which is something that is getting more and more important in the field these days. So Kitware works in a wide range of industries, and we have 5 main divisions at Kitware. We work on the computer vision field, where we treat a lot of videos, as well as data analytics, and scientific computing with toolkits that we have developed on applications such as VTK and PowerView, and in the medical computing field. The software solutions team is dealing with all the software process and is also responsible for the maintenance of CMake. And we also help our customers and the community to get in the hands of CMake and works a little bit better with CMake. One thing we do at Kitware is that we develop platforms and solutions that are based on open source software. We are known mostly for VTK, the visualization toolkit, which was developed in the early days of Kitware and keep growing. We also are developing ITK, the Insight toolkits, as well as PowerView, and we are the main developers and maintainer of CMake. One particularity about Kitware, about what we do, is that we develop toolkits as well as applications. But our toolkits are mostly C++, and they have a little bit of particularities that they are cross-platform. So they have to run on any type of operating system, Linux, Mac, Windows, and also embedded systems sometimes, as well as mobile devices. And also they have to work on a wide range of devices, such as web, desktop, mobile, cloud, and high-performance computing. So that makes our life a little bit interesting, and that requires for us to develop tools that allows us to quickly develop on cross-platform functionalities. So for that, we started with CMake, and CMake actually started in 99, 2000 in the year. It was developed initially for the Insight segmentation and registration toolkit, ITK. ITK is a toolkit meant for medical image processing. It was funded by the National Library of Medicine, branch of NIH in the US, and it's part of the Visible Human Project. The Visible Human Project is actually a kind of a interesting project that started in the 90s, where someone gave his body to science, and then he was scanned, first CAT scan, high resolution at the time, as well as MRI, so magnetic resonance imaging, as well as slices of his body. So his body was put lay down. It was actually frozen, and it was sliced and imaged photography. This is what you can see on the top right corner of this slide. And this data was, the acquisition was controversial. The project was a little bit controversial, but also it was a huge success because it provided for the scientific community the first of its kind data sets. And in 99, the NLM looked a little bit at how the data sets were used, and a lot of engineers and researchers across the world were using developing algorithms to do image processing on this data. Image processing such as segmentation, so trying to figure out part of the body and extract part of the body in the digital way, as well as registration, what we call fusion. So trying to fuse a CAT scan with MRI scan to collect the information, put them together. And so the NLM decided to quickly to develop a framework that will allow to have a common platform for developing these algorithms. So instead of having two groups across the world developing their own algorithms in their corner, to put that together, and they decided to create the Insight Toolkit. So the Insight Toolkit is based C++. It's an open source toolkit. It's available actually at itk.org. And it was a consortium initially was part of academia and part of industry, and Kitware was involved with this. And one of the first tasks that Kitware had was actually to develop a tool or way for this toolkit to be compiled. This toolkit, C++ toolkit, was meant to be used and compiled because it's not an application by a lot of users and researchers that don't necessarily know about build system or compilations. So it was very important for them to be able to easily compile the code. So the three main platforms were Linux, Mac, and Windows. And at the time, VTK, it happened, had a tool called PC Maker. So that was generating Visual Studio projects. So that's how CMake, since pretty much day one, had a way to generate Visual Studio projects, which was the unique feature that CMake had at the time. And then it grew quite a bit. So CMake, the 1.0 branch was created in 2001. And then it grew from there, and we'll discuss a little bit about that. So what is CMake? CMake is a cross-platform, so it works on a wide variety of platforms. And when we say platform, it's a combination of operating system, but also hardware that you might have, as well as the build toolchains that you might have as well. It's open source. It's released under BSD license, and it's a build system generator, meaning that it's going to generate for your build system, and depending on what you have, it's going to do that. One particularity about CMake is that actually it has to run on a wide range of platforms that I was mentioning, and we are testing that every day. So we C-test on C-. We've been developing ways also to test CMake, and it happened that it helps us also to test on our other software. From day one, the goal of CMake was, and the philosophy we had, was to let the developer use their native development tools that they love the most. The main reason for that is, instead of imposing the compiler, the tool chains, and the IDE, we wanted to let everyone use what they loved, because we think first they are more productive this way, and they don't have to relearn the tool, but also they are able to just keep what they have and use the toolkit. So the adoption, actually, not of CMake itself, but the adoption of the toolkits that will be used will be greater. So that was a philosophy we try to keep, and that's why CMake is this way now. And it doesn't do, it's not perfect, but we are trying to make it better every day for that. So CMake, for those who don't really have touched CMake and know what how it works, CMake takes plain text files as inputs. So basically files that are called cmakelist.txt to describe your project. And what it does is, when you run it, it will produce project files or make files. So project files will be for Xcode, for instance, or Visual Studio, and make files, we support quite a bit of make files as well. And CMake is also a family of software development tools. So of course, for the build, we have CMake, but we have also companion tools such as CTest and CDash for testing, and packaging, we have also CPack. So CPack is bundled with CMake. If you download CMake, you probably have CPack installed with it. If you compile it yourself, you have an option to compile CPack. It's a very lightweight executable that allows you to create professional platform-specific installer. That's what we use for delivering CMake, and it will provide Windows, Mac, and also on Unix, it will support package manager, such as Xeon, APT, and so on. So it's a nice way to deliver your application, so being closer to continuous delivery. We use that also for applications that we have at Kitware, such as PowerView and others. And again, if you use CMake in your project, using CPack is actually fairly simple. In about 10 lines of CPack code or CMake code that you add in your code, CMake list files, you are able to have a packager. Of course, it doesn't do everything potentially, but it will solve most of the packaging problem or solutions that you want to have. Another companion application that we have to CMake is CTest. So CTest is not a unit testing framework, as its name might suggest, but it's actually a testing driver, meaning that it will take your unit testing framework, and I say unit testing, it could be functional testing, any testing framework basically, and it will drive it. It will drive the tests, it will run them, it will collect the information, and then you can do what you want with it. You can check if the output is correct or not. What we do here at Kitware is we use it a companion with another tool that we have called CDash, which is a web-based dashboard for collecting testing results from CTest. The screenshot that you see is an example of what we have. So each line, for instance, is a different configuration that we test. For CMake, we have 100 builds that are generated every night, where we test continuously this based on merge requests, but also on a nightly basis, and we drive the packaging as well. So CDash is not going to drive your test itself. CTest will do that for you, and some people use it in combinations with Jenkins, for instance, or Travis CI or Circle CI and other CI tools. But it's a nice way to display and show the testing results. At Kitware, we work a lot in the visualization fields. So when, for instance, you have a rendering that fails a couple of pixels, you need to be able to show that, and you need to be able to explore what's going on. So CDash will provide you that in a web manner to do that. So one thing we wanted to do with CMake is, and the analogy we take sometimes is we wanted to change the way we build C++. So interpreting languages, some interpreting languages, they solve a little bit the cross-platform way by making you install an application that will do the interpretation of your language, so make it portable by default. And the same way that Boost aims to give C++ that set of useful libraries to be able to use them, like Java, Python, or C# or .NET framework, we wanted CMake to aims at giving this C++ portability, like the compile once, run everywhere that these languages have. And it's obviously not an easy task. We've been facing challenges, but the community has been really helping, and we've been improving on top of that. The idea is to have the same build tool and files for all the platforms. We all know that it's not always possible, that you need to have sometimes a platform-specific ways of compiling, but at least provide a unified framework for that. And it should be also easy to mix both large and small libraries. That's something we wanted to have as well. So the key CMake aspect and the vision of CMake is basically that we want to only depend on the compiler. We didn't want to have to rely on other things than a compiler, and that's why if some of you have been using CMake, the first thing that when you run CMake for the first time, the first thing that it does is actually checking which compiler you have and how this compiler works, and basically defining this compiler. Which could be obviously tricky for when you do cross compilation sometimes, but that's a different story. We want also CMake to work on any type of OS compiler on ID that will support C++. So of course, the CMake team, development team is limited. So supporting that at the greater scale requires community efforts. So that's why we rely on the community to be able to help us supporting new compiler, new IDs, and new operating system as well. And the goal is to allow linking not only for small projects, but also for large projects, and being able to do that in a seamless way, I'm going to say, but also to be able to do that so that everyone can use it. So CMake supports a wide range of tools, native tools. We support actually pretty much all the version of Visual Studio, starting from Visual Studio 6, and we are deprecating them as we go. But even 8 days ago, Microsoft announced that 2022 we support CMake. We talk a little bit about that. We support Borland Make, another type of make file, Ninja, Xcode as well. And we support quite a bit of IDEs. Most of these IDEs actually have been contributed by the community. So CMake is able to generate for this IDE. What we're seeing also now is that some IDEs, they will integrate CMake. So they will make themselves basically understand CMake, which is pretty nice to see on that. So one thing about CMake is also that CMake, it's a build system generator. So the part of the generator is important. It means that it's not a build system itself. So it has to adapt to new technologies, new IDEs, and new compilers. So for instance, we work with Microsoft on the Visual Studio team to have they have team working on CMake that has releases supports basically the new version of Visual Studio is supported after the beta comes out. The same with Apple on Xcode. Basically, weeks after the beta comes out, CMake will be supported. We work with the Google team and the Ninja team to support a little bit more CMake as Ninja matured. And with the recent shift also with Apple Silicon, we've been having support with that, being able to support that. And also, we work with compiler providers and Clang, GCC, Intel, and others to be able to support new version of the compilers, meaning making sure that CMake understands this new compiler and improving that. CMake is actually also quite popular. According to the JetBrains IDE, CMake is the most popular build tools at 53%. It went up from 82%, 42%, sorry, a year ago, which is great to see. And it's getting a lot of traction. So a lot of people are starting to use CMake, and especially for C++ projects. So about over 90% of the code that CMake deals with is C++. We have also, of course, CUDA and all the NVIDIA efforts that are supported, a little bit C#, Fortran as well, and a little bit some other languages that are a little bit more exotic that are not totally supported, or that are a smaller version of people are using. We also, I think about 3 years ago, we looked at job openings with CMake experience on Indeed, on LinkedIn, and just to see which company was looking for CMake developers or CMake understanding CMake or CMake expertise. And there are quite a lot actually that are large corporations, small corporations, actually a startup as well, looking for CMake jobs. So which is great to see. It's great to see that CMake is popular. One thing I want to reiterate is CMake is definitely a community effort. The team here at Kitware that supports and develops CMake is fairly small, but we have great developers here, and we also provide support on training on top of that. But there is really a community. There are books that are released. There are presentations at conferences about CMake and how to use CMake, sharing experiences about CMake. All of this is great way to disseminate. And I mean, the goal of what we had in mind with CMake was to release an open source build system generator that will work for everyone. So that's our goal. We're not saying that CMake is going to continue to grow, and we are fairly flexible in trying to make it work for everyone. We know that we cannot please everyone. There are some projects that it might be difficult to transition to CMake, but most of the time we should be able to do so. And the community has been growing so quite a bit. And in this slide, the comparison with Auto Tools is actually probably not fair. But we've seen what is interesting in the blue graph that shows that in Google Trends, it goes back to 2004, but it shows that CMake has been growing in interest quite a bit, and the community as well has been growing, as we can see. You will see a small step around 2006 in that graph. That's when KDE, the K-Desktop Environment, announced that they were transitioning to CMake. So they have been looking at, they were using AutoConf, and then they moved to Python, to SCons, sorry, they try SCons, and then they finally decide to move to CMake. And we still have the announcement somewhere. It was great for CMake on the community, and starting from there is like snowball into a lot of people using it, including large corporations. Netflix have been using CMake, CTest, and CDash for testing their streaming services, for instance, to check the quality of the streaming. And they released a small blog about this in 2014. So we are looking forward for the next decade of CMake potentially growing and adapting, and we know there will be some challenging there, and working with the C++ community and others to make sure that we adapt. So CMake is very important. So we can ask why CMake is popular, and actually, I mean, if some of you have used CMake, getting started with CMake is actually very easy. The level of entry is very easy. With simple commands like add library, add executable, you are able to do, again, cross-platform, being able to generate a library and being able to generate an executable with one line of code. I mean, you need a little bit more of that, but basically with one line of code, you are able to generate that. Also, because we are cross-platform, because CMake is cross-platform, you are able to generate, we are able to touch more parties and more users that would be using CMake. And we have even some Windows-only developers that are using CMake, because CMake is a little bit easier to manage and to support than just staying with the Visual Studio, for instance, only applications. And a lot happens with these simple commands that we have. A lot happens behind the scene that are handled by CMake, and basically you're trusting CMake to do the right thing there. And there is a lot to do. But most of the C++ nowadays projects that are starting, a lot of them are using CMake. So along the way, we have some unlikely but pretty cool contributors. to CMake. One of them is in the recent years, we had a collaboration with Minecraft. So if you have kids or if you are younger than me and you play Minecraft, this game is actually set up with built with CMake because it has to run on multiple platforms. So it's been a great way for us to basically get into the Minecraft, the collaboration, and of course challenges because it's a fairly large project and so on to work with that. Also, starting 2017, Visual Studio 2017, Microsoft is now shipping CMake with Visual Studio, which is great, especially considering that not so long ago we were reverse engineering the Visual Studio project files to make sure that they run with CMake. So it's been very interesting way to do that, and thanks to the Microsoft team for helping us with this and making sure that we are working on that, and they are also helping us on the module support, for instance. We'll show that to you a little bit later. It's been a great addition to CMake and also for the developers around the world to be able to do that, especially the one using Visual Studio. We also work with Bloomberg Engineering. So they added a couple of support, like the improvement to the extended COF object file definitions, for instance, or improving also the CMake's file-based API that they needed again for their project, and that we put in CMake 320 not so long ago. Again, these are examples of community supported. So these are functionalities that are needed for some big project, but also that are used for other projects. And it's great to see that. And the Qt company also is helping us. I describe some of these as well. So I'm not going to go into too much detail about coding with CMake. If you're interested, I provide some resources at the end of this presentation. I just wanted to just show a little bit for if some of you don't know really about CMake, how it works. But the way it works is you have your C++ code. So instead of writing a make file or writing or having your Visual Studio or Xcode generate the make files for you or project files, basically you will describe your project. So what you want to do, what are the targets, what are the dependencies between the targets, some properties, and so on. You will describe that in text files that will be along with your source code in your project. And then on each platform, you will have CMake installed. So what I want to mention about CMake is that CMake is actually a fairly light executable. It's written, it's meant to be cross-platform, so to work pretty much anywhere, and you can compile it, assuming that you have a C++ compiler. And it's fairly easy. And it's plain text files, so it's fairly easy to understand and to parse for CMake. And you will run that. There is a configuration step, and there is also a generation step. Again, I won't go into too much detail into that. But basically, at the end, once you run CMake and you configure your projects, you will be able to, you will have a make file, or you will have a project file that you can run. And then you launch your favorite IDE, Qt Creator, CLion, for instance, and you can compile your project. It will exactly know what to do. That's the main idea behind CMake. There are a couple of ways to run CMake. There is a Qt GUI that is a cross-platform again, called CMake GUI, that allows you to show that to your developer, to show the options. So, for instance, do you want to build the documentation? Do you want to build testing? Do you want to have specific configuration along the tree? You can specify that in the CMake GUI. There is also terminal CLI, CMake, that will allow you to do that. And there is also, you can run CMake from the command line as a non-interactive command line. So basically, being able to run CMake, again, there is a configuration step and the generation step as well. So this is an example of the CMake workflow. So basically, the first thing that you will do, you will run CMake, and if you can see from this slide, what CMake does is checking which compiler you have, and it would check do a small configurations, check that your compiler, and then it will go into the configuration, and then it will generate the make files. You can also call CMake dash dash builds that will call your toolchain, and that will compile your project automatically. And then also you can run testing if you have testing for that. So again, I'm not going to go into too much detail about how to use CMake. I hope I gave you some overview of what CMake is for people who don't know what CMake does. It's available at cmake.org, so you can check that. There is also documentation, and again, there are tutorials online that are available, and Kitwe also does training if you're interested, as well as support. So now I'm going to talk a little bit more about something that we've been pushing in the past years about CMake and the relation with C++20 modules, which is something that we are very excited, and a lot in the community, I think, are excited about C++ modules. But we need to find a way to support that. So I'm pretty sure everyone knows how module works, but this is a very light example of that. So let's say you have an hello world CPP file that has a module declaration. So we export the hello world, and we have an export declaration that export the function hello. In your main.cpp, you will do an import declaration, and then you will be able to call that function. Okay, this is great, but from a build system perspective, you need to know the dependencies. You need to know that you have to compile hello world.cpp before main.cpp. Otherwise, the compiler will not work. And that's something that without parsing the code or having information from the C++ compiler, you cannot infer that. So basically, you need to have an external int, and CMake doesn't have a parser, a C++ parser, and we don't want to have one. So we need to have an int how to build that on the order of dependencies. So the good news is, well, CMake has been doing modules for quite a long time, over 60 years actually. And one reason for that is because we've been dealing with Fortran. So Kitware works a lot with the national labs, the US national labs, and in the scientific community, a lot of Fortran code base and mixing with C++ as well, and they have been using CMake. So what happened is that in 2005, there was an initial makefile support for modules that was added to CMake by Brad King, actually, at Kitware. And that was added that, and I'm going to describe a little bit how it works, but it was added to CMake. It was working pretty well. And then 10 years later, we started to add support to Ninja for Fortran dependency file. This was funded as part of the Trinos projects from Sandia National Labs. And the way it's been done is basically we had to fork Ninja, and we had to put the functionality there and be able to support the modules. The good news is that 4 years later, seeing that it was actually working well on the fork Ninja for this Trinos project. Trinos is a very large project, by the way. It has quite a bit of dependencies. The build tree is actually pretty complicated, and with the forked that we have a Ninja, it will show that actually Fortran modules were working pretty well. So what happened in 2019, Ninja, they merged all the changes upstream to support Fortran, but that was done because also of C++ module, and they knew that C++ modules were coming, and the system would work for that. So how do we handle that in CMake for Fortran? And then I talk a little bit more about the translation and how that can be done in C++ when we move there. But so let's say you have a module math here, and when you compile it in Fortran, it will generate a module implementation of object file, math.o. But it will also generate a math.mod, which is a module interface file. And this file will be actually used by your program main, so to generate main.o. So basically, you need to have main.o to generate, sorry, you need to have math.mod to generate your main.o. So the build system, it must discover this dependency in order to build and rebuild the program correctly. Okay. So building the program correctly, meaning that it has all the information, and rebuild, meaning that if something changed, it has to know the dependency and do it correctly. But also, if something doesn't change, we don't want to rebuild all the time. We just want to rebuild what's needed. So how does it work for CMake? So CMake is a target-based system. So basically, in a CMake project, we organize the source files into groups that are called targets. I mean, if you've done make files, that's pretty much what it is. And each target basically corresponds to a final build artifact. A correct build, so what we want at the end is a correct build. That means when the source file is changed, all the outputs which are affected by the source's contents have to be recreated. And so that's the first thing that we want. And we want an efficient build, like I was saying before, is that means that any outputs which are not affected by the source changes shouldn't be recreated. And we don't want to lose precious CPU time to recompile something that was not needed. So if we look at the build graph for a single source for our Fortran module dependency, we can look at the F90 original source. What's happening is that we have a preprocessor. So the build system has to preprocess the source file to extract the module dependencies. And the build system may preprocess the source file independently and concurrently, because these are, especially in Fortran, these are independent of the module constructs. So we should be able to do that. The preprocess rule, what it does, it's performed by compilers in our case, and it handles the resolution of the include and the define directives, for instance. And during the execution of this rule, basically CMake expects that there is a header dependency information that is going to be available. And that stores in pp.f90 file, preprocess source. So what we do after that, we do a scan rule, which is basically performed by CMake. And this scan rule will extract what we call the required and provides modules for a source file, and we store that in a DDI extension. And once we have this DDI, we perform a collate rule. Again, this is performed by CMake, and this is to collect information on all the scan rules that you might have for your files. And we collect that, collect all the information, also collect rules about the dependent targets, and we write a module dependency information called DD file, dynamic dependency file. And then once we are ready to compile, we looked at this dynamic dependency file. And one thing to realize here, and the arrow that you see, the blue arrow, means that basically the compile rule cannot be run until the build tool that we are using takes the output of the collate rule. So we have to, the order has to be that the collate, all the information about the collate has to be available for the compile to run. So this is something very, very important, and that is what's going to define the order. So if we look at the graph for a single target, you will see that, for instance, if we have three source files, A1, A2, A3, we will do the same thing, the pre-process, as usual, the scan, and we collate all the scan files, output, and then we use that to compile. So what you see in this graph, actually, there is interdependency between the compilation output that will be discovered during the build. So you remember at CMake is when configure, generate, and then you delegate to the build time. So at build time, you have to understand that. And that's why we had to modify Ninja, so that Ninja is able to handle these dynamic dependencies. You will note also that in this graph, there is no interdependency between the compilation and output. So if there are any, they will be discovered during the build. And that's what we show here is that basically you have a mass.mode that is needed for the object A2 to be compiled. That will be discovered by Ninja at build time. And this graph shows a little bit. It shows that when a.dd, which is basically our output of the collect file that has all the information we need for the dependency, when it's up to date and we can read it, we'll discover a lot about our build graph, and the build system will understand everything about the build graph. And what we can see quickly here is that first A1 and A3 can be compiled separately. That A2 depends on A1 at this step, and we have that. And more importantly is that if something has changed in A1, we might have to recompile A2, but A3 should be good. And again, all of this is discovered by CMake and by Ninja in that case, and we are able to deal with this dependency. And then it gets a little bit more complex when we do a build graph on multiple targets. So then one thing we added is that the DD file, actually, the dynamic dependency files for direct dependent targets, they are actually additional input to the targets. So that means that modules that are contained within a source file in library B, for instance, that will be used in another source file in library C, we will get the dependency correctly for that. So I hope that gives a brief overview on how the dependencies handle on the multiple steps that we have, the scan and the collate, and that does this job. So how does CMake handles the modules? So basically, we have a Fortran parser that is based off make dep F90, which is a make dependency Fortran 90 applications. It's a Fortran parser. It's not perfect, but it works pretty well. That's one thing we want to try to avoid, having a parser in CMake, but I touch base on that in 2 seconds. We had to patch Ninja, and now that's upstream, so that's pretty good. And we have also a dynamic dependency collator inside CMake that is available, and this one could be reused for C++. So for the C++ module, actually, we can do exactly the same. I mean, we can if we have help from the C++ compiler, we can have the C++ build graph, and we should be able to skip the pre-process form. So basically, we can just have a scan and collate, and it will work pretty well, exactly the same as we've seen with Fortran code. And it will also work with compiled code generators as well. So let's say you have J1 CPP.cpp here that generates an executable, that this executable is run at build time to generate code, this A3 code. We can do the same. We can do a scan and collect on this, generate the code, and then scan and collect on the build system generate on the A1, A2, and 3. and then generate the dynamic dependency file for that, and it will work exactly the same. So we are very confident, and I'll talk a little bit more about that, but we are very confident that what we have done for Fortran actually will work for C++, for C++ modules. So there are basically options, and we wrote as part of the C++ standard, we wrote some recommendation, but there are some ways to scan and collate. So one option is to scan the sources independently, then collect them. And that might be preferred when you have incremental builds with a small number of change files, because the scan rules on build file will only be done when necessary. It might be recommended for project with wide build graphs, where the number of scan steps at a given build graph depth can saturate the build machine setup. And also a project with a lot of generated sources, obviously. Another option is to scan source all at once and then collect. So that's something that is possible as well. That might be preferred when we have from scratch builds, and when we have also a platform with expensive process execution, because you run only once the scan. Of course, this step will require a more complex scan tool. Because internally you should decide whether or not to update the output file, depending on the source, to avoid rerunning other rules unnecessarily. So we need to be a little bit careful on that. It would require a smart scan tool. And the last option is we can scan the sources and collect all at once. So this is probably the more extreme version of the previous examples, and we'll need more complexity for that. So the message here is that we don't want to put C++ parser in CMake, because we feel that, well, first, like the compiler are doing that already, so we don't need to redo that. We also learned from Fortran that well, we need to maintain that, and when the language evolves, we need to make that evolve, and the compiler should be doing that. So basically, we need compilers to provide support for that, and we think that the scan rule that has to be implemented can be implemented as phase 4 of the compiler. And ideally, the compiler will provide the name of the module to be imported and exported, the name of the header units that are imported. So basically defining the dependencies and the path of the file that are read by the preprocessors. And if we have that information, we should be able to take that, and the build system should know the dependency, and we should be good. So we wrote, as I was saying, we wrote a couple of references and the C++ standard that are done, and actually Visual Studio released in 2022, and their version of Visual Studio 2022, they released a version of the scan version that seems to work. We tested it. There are a couple of tweaks that we need to do in CMake, but it seems to implement that. So we are hoping that we will have support for GCC and others in the short future for that. So hopefully it will work great. Next, I'm going to talk about CMake and dependencies. So as you know, when you build software, most of the software, they are not independent. They are usually depending on quite a few other libraries that are needed. In our domain, for instance, for HPC simulations, so high performance computing simulations, there are quite a bit of libraries that are developed for that. So for instance, either finite element libraries and neural nets libraries for HPC, and they usually rely on on a lot of packages. So like MFEM relies on 31 packages. MUMMI, which is a cancer drug interaction modeling system for high performance computing, they rely on almost 100 packages and a lot of dependency edges there. So it's a little bit tricky. The way we try to handle that with CMake is basically with the notion of find package, which has been around forever. So let's say you have a library foo and you need PNG. You would do a find package PNG, and then you will compile your library, and then you would use the target link libraries foo and include PNG. And the nice thing with CMake is that actually everything is doing well. It will not matter if the target has been installed, if the target is a package, or if the target is actually sources that you are building. CMake, it should be transparent for CMake. So CMake provides about 150 find modules. If you type CMake --self module list, you will get them. But the question we have is, and we had, I mean, actually in the past years, is how do we maintain these modules? So what happened is people will develop find packages, we will put them in CMake, and then it will happen that these packages will not be supported. So new version will be released, and we would not have being able to support this version because either the developer is moving on or we cannot keep up with it. Up to like maybe 5 years or 10 years ago, I would say that the idea was to create a full repository where people can commit these find modules, can help maintaining them. It never happened, but a better solution we realized, especially with what we call modern CMake, it's to export the targets. So let's the third-party application, in my case, in my example, the PNG library, if it's using CMake and using the install rules of CMake, actually CMake can generate imported targets for another application to use my PNG library. And because I'm the developer of that PNG library, I know exactly what should be installed, what you need to use that PNG library. And in that case, I will be able to provide that and provide all the information for CMake to run. And that's what we do with the install export commands that we generate the library, but also generate the targets. So the definition of the targets so that CMake can re-import them and use them. This is important and this is great. And what we do is we encourage people to that are maintaining third-party libraries that are meant to be used by other applications to use exporting targets. And coming back to exporting targets, it's not something that is necessarily very easy to do, depending on the complexity of your project, but that's something that you can definitely do. There is pretty good documentation online for how to do that. A couple of other ways also to add third-party into your CMake project is to use what we call external projects, or also called super builds. So that basically will allow you to build on importing targets at build time. So this is something also that is fairly important for CMake. So in this example, we point to a Git repository with a Git tab, and we just add build time. So when you type make, it will download and it will build that repository. Not that the repository doesn't have to be CMake based. It could be it could have Makefile, it could have a different build system. It will work as well. It should work as well. In 3.11, CMake 3.11, we added something similar to super build, which is called fetch content. And this is basically, you will see the signature is very similar to the previous external project add. But basically, it's a way to fetch the content at configure time so that they are available when you configure. And it's a nice way to do that, being able to deal with that. So also that CMake provides all the functionality to under project dependency with external project, fetch content, or they will never replace, CMake will not replace packages, package managers. So if you have complex software, you might be able to handle it, and we do that, for instance, for PowerView. we handle it with super builds, but especially if you use different packages, different languages, package managers are the solutions for that. So Conan, for instance, VCPKG, and Spack are all good options for managing these large C++ projects. So Conan, if some of you probably know that, but it's based on CMake, and what they do now, starting in a newer version, they're now able to generate this configure file for CMake, so that your package can actually be used by other applications using CMake. Spack. So Spack is a package manager for supercomputers, but it actually also allows you to, you don't have to use a supercomputer, but being able to use it on other platforms. So that's something also that is very promising. And Spack claim of fame is also for some code at Lawrence Livermore National Labs. Using PyTorch, it goes from days to configure a project to about 20 minutes. So a huge improvement there. And at Kitware, we've also been working with the Spack team to work Spack on Windows, which is we think it's going to be great. So a couple of things just to reflect a little bit on the future of what we like to see for CMake is, as I was mentioning, we like to see to have all the C++ compiler provide this built-in interface for the C++ module, and also have a standard for cross-platform information for the CMake config file, so that the packages can be known by CMake as well. I'm going to go next over new CMake features that we've developed. That the community has been developing. So in collaboration with Microsoft, we actually introduced, starting in CMake 3.19, presets. So basically, it's a JSON file, because CMake presets.json, that allows you to specify the build directory, the generator, the cache variables, all the information about your builds. If you wanted to build on different compiler, most of the time you will have to define your environment, different environments, or create shell files, shell scripts. Nowadays, presets allows you to do that. So you can use a preset either from the user interface or from the command line with list presets. And then you can use that preset with the -- preset command, or directly from the command line by selecting your presets. We added also a couple of new features, and thanks for to the Qt company for supporting these developments. As you probably know, Qt is moving from CMake to CMake, which is great, and improving CMake. So we added to support speed up compilation, the target precompilators commands, available since 3.16. So basically allowing you to do precompilators. We have also done Unity builds, so basically creating one source file to speed up the builds. There is a documentation on these, couple of options that you can set as well to set the size of the Unity build and so on. Again, available since CMake 3.16. So most of you, if you've been up to date with CMake, probably know that what it does. We also introduced in CMake 3.17, we introduced support for Ninja multi-configuration. So before, if you wanted to have a configuration like debug and release on Ninja, you needed to have two drill trees. Now with the Ninja multi-config, you can just have multiple configurations in the same drill tree for Ninja. So it makes things a little bit easier for the developer to work with that. And we also added custom command updates for dependency files, for make files. So that has been done a little bit more recently in 3.20. We've done that. So that's almost the end of my presentation. I just wanted to give you some tips, and what, if you want to learn more about CMake. We at Kitware obviously do training, and I know some other companies as well are doing training, but we are also available for support as well. The way, if you want to learn a little bit more, what I would encourage you to do is not to copy CMake code from your friends unless it's recent code. When we do audits, we usually can flag that very quickly. But CMake is a language, so it's always evolving. So I encourage you to try to keep up with the language and learn a little bit. There are a lot of talks on modern CMake on YouTube and other platforms that are pretty well done. There are books. Craig Scott has been doing an excellent job on professional CMake. We have also a discourse forum that you can join, and you can look at the questions and ask questions and look at the answers. There are documentation that is always up to date. Not always perfect, but always up to date. And we have tutorials as well available on the website, cmake.org. There are technical guides that are available, and so tutorial on ways to do things. There are also other guides that are available out there on the web that you can find that are fairly easy to follow. And we have also adding ways to. We are testing within CMake the documentation. It's important for us to make sure that what is in CMake is able to work and is always compatible with the latest version of CMake that we release. So something very important. And one thing also is this year the book mastering CMake is now open, so you can download it. You can download the PDF if you want to and look at it. We are still going to print a version that is going to be a little bit more lightweight if you like paper copy. But otherwise, it's available. If you want to contribute, you are welcome to. And again, this CMake is a language, so keep in mind that it evolves. And if you need more information, feel free to contact me. Thank you very much, and I wish you a great rest of the Meaning C++ conference. Thank you.